Good evening, everyone, and welcome to this evening's inaugural Islands of Idea event, which is a new UTAS initiative for online seminars. And tonight's seminar is Oceans, Ice and Climate Change, an IPCC update. Firstly, I'll just introduce myself. My name is Terry Bailey, and I have the pleasure of being the Executive Director at the Institute for Marine and Antarctic Studies at the University of Tasmania, and I'll be your host for tonight. Before we start, what I did want to do was make an acknowledgement of country, which is really for us a reflection of this institution's recognition of the deep history and culture of this island. And in that sense, the University of Tasmania wishes to acknowledge the Muwina and the Palawa peoples, the traditional owners and custodians of the land upon which the campus is built, and to pay respects to elders past, present and emerging. And I also pay respects to Aboriginal and Torres Strait Islander people joining us tonight. Just as we kick off the event, I did want to run through a couple of housekeeping notes. Firstly, just so you're aware, microphones, videos, chat functions, and the raised hand function have all been disabled so that they don't cause distraction for the panelists. However, you can, as audience members, still send questions to the panelists using the Q&A function. And we've set a half hour aside towards the end of the presentation for a series of questions. The other, as we're all finding out in a COVID world and using a lot of Zoom, is occasionally people drop out. Please try and join back if that does happen. One other thing just to be aware of is that we are recording tonight's event so that it will be available later in terms of having access through YouTube or SoundCloud. Just as we begin tonight's event, I wanted to just mention a little bit about the role of the Intergovernmental Panel on Climate Change, which we all flippantly run through as the IPCC. But the IPCC prepares comprehensive assessment reports around the state of scientific, technical and social economic knowledge on climate change, its impacts and future risks, and the options for reducing the rate at which climate change is taking place. So the IPCC, as we all know, is an incredibly important forum, and we're delighted tonight to have two IPCC authors joining us. Firstly, I'll introduce Professor Nathan Bindoff. Nathan is one of the world's leading climate scientists and a physical oceanographer. He has studied signals of change in the ocean through measurement in things like oxygen levels, temperature and salinity since the 1970s through to the present. His focus is on detecting and understanding the causes of change in the oceans. In 2019, he was the coordinating lead author for the 4th and 5th assessment reports for the IPCC. Nathan led the Oceans chapter in 2007 and the Detection and Attribution chapter in 2013. As a contributing author, Nathan was also part of the IPCC winning team in relation to the Nobel Prize that was shared by Gore in 2007. Professor Bindoff and his colleagues also developed the famous statement, "Global warming is unequivocal." Our second panellist tonight is Dr. Jess Melbourne-Thomas. And Jess grew up exploring Tasmania's coastline and wilderness and has gone on to work in the marine environment from the tropics to the poles. With a background in mathematical modelling and Antarctic climate change science, Jess is now a knowledge breaker at the CSIRO, helping to bridge the gap between complex science, research and decision making as it relates to sustainability. A passionate advocate for diversity and gender equality in science, Jess co-founded the Homeward Bound project, which took the largest ever female expedition on a leadership journey to Antarctica in 2016. Jess was one of Australia's first 30 superstars of STEM, and was named Tasmania's Young Tall Poppy of the Year in 2015 for her excellence in research, science, communication and policy engagement. Jess was also one of 12 female scientists globally to have her portrait featured as a constellation on the ceiling of New York's Grand Central Station as part of GE's Balance the Equation campaign. And further, in January this year, Jess was named Tasmania's Australian of the Year. In the silence of Zoom, on behalf of the audience, I'm delighted to welcome Nathan and Jess to present tonight's forum. Thank you.
Wow, thank you very much, Terry. Let us start. Thank you very much, Terry. It's a pleasure. There are 152 participants, which I think is extraordinary. What I'm and Jess are going to talk about in the next 40 to 50 minutes is about the latest report released on the 25th of September 2019. This report, which is about the oceans and cryosphere and changing climate, was actually the result of 4 years of planning and 2 years of hard work by 104 authors who developed the report as an assessment of an extraordinary amount of literature. The report has a key element in it, and that key element is called the Summary for Policymakers. The Summary for Policymakers in this particular report is about 14,000 words, so about 10 pages, 6 figures, and it has a couple of tables. And every word of that Summary for Policymakers was actually agreed to, line by line, by about 130 countries that were part of the IPCC. One of the key things that IPCC does is it engages with the governments of the world, and every government has what's called a focal point. And that focal point and their delegation were at this 4-day plenary session in Monaco, where every word was gabbled down, every figure and every table. And at the end of that marathon 4 days, some days actually being 24 hours long, resulted in actually a better summary for policymaker than actually went in. And it is truly remarkable how the governments actually engage with the researchers who are involved in this particular project to actually deliver this final report. And so in the next hour, we're going to talk about what all those governments agreed to. And let me just sort of show you the front cover of this report and the back cover. So on the left is the front cover. The front cover represents the polar regions, the Arctic, the Antarctic, the deep ocean, and the back cover represents the tropics, the coastal regions, our reefs, the areas that are low-lying, and then actually into the mountain regions. And together, these two figures really symbolise the content of this report that was actually commissioned by some governments from the world and agreed by IPCC to be undertaken. So the report really does cover all the aspects of water on the planet, from the highest mountains to the deepest oceans and from the equators to the pole. And what you can see in this slide actually is sort of a summary of the entire report. The key summary for policymakers that I just described, hammered out over a 4-day session in Monaco last year. The report covers mountain areas, and we won't talk about that specifically in this particular report, but it's actually the first time since 1995 when the high mountains have actually been covered. There are about 1 billion people that live in the high mountains, so it's actually an important part of the globe. But for today's talk, we'll focus on the polar regions, on sea level rise and some of its implications for low-lying islands. We'll talk about the changing ocean and marine ecosystems and its dependent communities, a little bit about the extremes, tipping points, and most importantly, some of the policy implications. Every chapter in this report is a sort of end-to-end discussion of the consequences of climate change in the oceans. It starts typically with the physical changes, but then rapidly moves to the impacts on marine ecosystems, on the ecosystems of high mountains or the polar regions, and then the consequences and whether they're observed impacts and our understanding of what those impacts mean for adaptation and solutions to the problems of climate change in the case of the oceans. The report is a collaboration of the researchers. There are 104 authors actually in this particular report who've led the development and writing of the report. There was an initial scoping meeting in 2016, which actually defined the shape of the report. This particular report was commissioned by several governments. They requested oceans, they requested a report on cryosphere, they requested a report on mountains, and what you get actually is one report that covers them all. The report is collaborative because we include contributing authors. There's another 300 to 400 people who contributed to the development of this report. Some 31% of the authors were actually women, and they come from, and collectively, all of the authors come from 36 countries, developed, undeveloped countries. So as part of the United Nations approach, we very carefully cover the distribution of the world, countries from the world with the right expertise, gender, diversity, and expertise itself. It's an extraordinary thing, a report that is relatively short compared to the full assessment reports that occur in this cycle. There are still 7,000 citable references around the changing climate in the oceans, cryosphere, and high mountains. And IPCC is very special because it really does have an open and transparent approach to the process of making these assessments. There are 3 independent rounds of review on each of the 3 official drafts. Each draft has experts and government reviewers, and the 31,000 comments that were actually received for those 6 chapters are responded to. Every comment is responded to, and when the report was published on the 25th of September last year, so also were the responses by the authors to the comments and criticisms and positive statements of the report. And as a consequence, you can actually track how the report evolved in response to requests from governments, comments by the scientific community. It's an extraordinary collaborative effort to undertake one of these reports. We don't start with start with a clean slate. Actually, in the 5th assessment report, we actually knew quite a lot about how the global oceans, the Antarctic ice sheet and the high mountains was actually changing. We know, for instance, that the Antarctic ice sheet has been losing mass. Greenland has been losing mass. That mass is transferring into the oceans through the rivers and through precipitation. It's increasing sea level, and sea level is going up. We know that the ocean provides key services to the Earth's energy balance by absorbing heat, by absorbing carbon dioxide from the excess carbon, about a third of the excess carbon dioxide from human emissions goes into the ocean. As a consequence, it causes pH to decline. And as the ocean stratifies, there's a tendency for the oxygen content of the oceans to decline. Not only are these things going on in the ocean, we know that the glaciers themselves are shrinking, snow cover itself has decreased and been attributed, and all of these things have been attributed to rising greenhouse gases and human activities in on the atmosphere. Permafrost temperatures are going up, marine ecosystems are actually changing. And what this report does is it builds on that earlier work, and it shows new expectations of how things have changed, whether it's in the physical system, in the marine ecosystems, or actually on human communities themselves. At the release of the report in Monaco, all of these things combined, of course, really means that the world's oceans and cryospheres have been taking the heat from climate change for decades, for many decades. And these changes, which have consequences on human communities and marine ecosystems, are actually quite sweeping and severe. And this is kind of a leading idea that comes from this total assessment of the world's literature around climate change in the oceans, cryosphere, and high mountains. Now, I'll just hand over to Jess to talk about the polar regions. Thank you, Jess.
Thanks, Nathan, and good evening, everyone. Thank you so much for joining us for this presentation. So I took my first plunge into the deep and dark waters of the IPCC with a newborn baby in one arm and a 2-year-old in the other arm. And trying to stay afloat was an interesting challenge. And the reason I thought I'd share that personal perspective on my involvement in the report is just, as Nathan has pointed out, to highlight that the IPCC has done and is doing a lot to support diversity in its author teams. And I was really fortunate to have support of highly experienced and expert authors like Nathan and others from Australia and internationally. So if you could go to the next slide, please, Nathan. Changes in the polar regions influence people's lives around the world, wherever they live. And findings from the SROCC report for the polar regions are, I think, striking and fairly concerning, not only with respect to physical and biological change in these regions, but also in terms of the impacts on human systems and our current capacity for policy responses. So the chapter reports that the Greenland and Antarctic ice sheets are losing mass. These ice sheets are now key drivers of sea level rise in addition to expansion of warming water, and because ice sheets will continue to melt in response to past and current warming, the planet will experience global sea level rise for decades and centuries to come. Arctic sea ice is declining now in every month of the year and is getting thinner. And if global warming is stabilised at 1.5 degrees above pre-industrial levels, then the Arctic Ocean would only be ice-free in September, which is the month with the least ice once in every 100 years. But for global warming of 2 degrees Celsius, this would occur up to 1 year in 3. So quite a striking difference. Climate change in the Arctic and Antarctica is already influencing polar region ecosystems, and that has cascading impacts for marine resources and the communities that depend on them, as well as implications for food provision at the global scale. And the governance landscape for polar regions, it was assessed as not being sufficient currently to address cascading risks and uncertainty in an integrated and precautionary way within existing legal and policy frameworks. So next slide, please, Nathan. The changes in ocean and ice environments in Antarctica and the Southern Ocean are diverse and also unique at a global scale. And this summary figure illustrates that while Some features and processes have changed as a result of climate change, particularly warming of surface waters in the north of the Southern Ocean and cooling and freshening in the south, strengthening of westerly winds, change in the volume of Antarctic bottom water and an intensified eddy field. Other variables, notably sea ice cover, haven't changed in a detectable way. And as you can see in the bottom right here, the Southern Ocean plays a disproportionate role in global ocean heat gain and that proportion has actually increased in recent years. So if we go to the next slide now, there's a graphic that summarises the impacts of climate change on key elements of Southern Ocean ecosystems. And the way to interpret this figure is that the blue boxes show a positive impact of climate change. The purple boxes show mixed positive and negative impacts, and an orange box is a negative effect. And the white dots show the level of confidence that we have in that assessment from the scientific literature. So the high-level messages here are that projected warming of the Southern Ocean and acidification will have negative consequences for many groups, particularly Antarctic krill. That some species of marine mammals and birds are winners while others are losers, and that depends on the way that they use different ocean and ice habitats. And then finally, close to the Antarctic coast, we are currently seeing some positive ecosystem impacts because as ice shelves break up, they let more light through to the ocean and support productivity, and also can create new habitats for a range of organisms. So in the next figure, we have a similar representation. This is a summary figure from the Summary for Policymakers of the report, and it places those changes that I've just talked about for the polar regions in the context of changes and impacts for all regions of the globe, and they're listed across the top there. So we have a similar style in terms of interpretation. Across the top, the yellow boxes indicate an increase in a physical variable due to climate change. Green is a decrease, and we can also have mixed effects where we see both increases and decreases. And then the bottom parts of the figure are the impacts of those physical changes for ecosystems, and at the bottom for human systems. So if we start along the top, then you can see that the physical changes are actually fairly consistent across all regions of the globe, except that sea ice is decreasing in the Arctic with high confidence, and that there are mixed changes in the Southern Ocean and much lower levels of confidence. And then in the bottom part of the figure, really the most striking thing is that there's a lot of red, indicating that for ecosystems and for ecosystem services, almost everywhere that was assessed, there was a pervasive negative impact of climate-driven change. But interestingly, the polar regions, which are the ones highlighted with the red rectangles, you see that there's some blue creeping in, so there's some evidence of positive impacts. And one part of the explanation for that is that warming oceans are driving species away from the equator and towards the poles. Nathan will talk more about that. And that means that there are new fish stocks in polar regions that can be targeted by fisheries. There's also increased light availability, as I mentioned, as sea ice and ice shelves melt, and that has some positive impacts for marine species. And it also means that these regions are now more accessible to tourism and to shipping. And so I'll finish up by just by noting that this is a summary assessment of observed changes to date, and that the picture may start to look very different as we look to the future. Back to you, Nathan.
Thank you very much. Thank you very much, Jess. So So Jess has highlighted the polar regions, and one of the drivers of sea level rise is the acceleration in the loss of mass by Antarctica, Greenland, and by the loss of glacier mountains. But another driver of sea level rise is actually the uptake of heat and the thermal expansion that goes with it. And these three things, the mass loss from the ice sheets, glaciers, and the expansion of the oceans, is what actually contributes to sea level rise. And as illustrated in this figure, actually there are about 65 million in small island developing states that are affected by sea level rise, that are at risk from sea level rise. There's a further 680 million who live in low-lying coastal regions. So a very significant fraction of the global population actually lives right in the coastal regions where sea level matters. And so they're vulnerable to sea level rise. And here is a figure of our understanding of the contributors to sea level rise at the global scale. And in a moment, I'll also talk about extremes, the sort of extremes you saw in that picture a moment ago. Greenland, Antarctica, and glacier mass loss are now actually the biggest drivers of the rising sea level through to 2100 and out at 2300. When I started IPCC, the largest driver in 2004 was thermal expansion of the water column. But now the biggest, even though 90% of the Earth's energy goes into the oceans, even though most of the energy goes into the oceans, it's not thermal expansion anymore. It is actually the mass loss, the melt of Greenland, the melt of Antarctica, and from glaciers that are actually driving most of the signal of sea level rise that we currently observe in the record of instrumental record from the 1990s through to 2020. The projections of sea level rise also have been added together to give this total combined sea level rise out to 2300. And this report, for the first time, has actually put what the projections of sea level rise are out to 2300. And it was demanded by the governments. So the governments surprisingly cared as to see what the future risk of sea level rise was for policy relevant high emission scenario and also a low emission scenario. The lower emission scenario is actually one that would lead to a world with a 2-degree global temperature change as agreed in the Kyoto Protocol, and the Paris Agreement asked for a higher ambition of 1.5 degrees, which would lead to a slightly lower sea level rise for the low emission scenario. What you can see here is that in a high emission scenario, we'd have something like 0.84 metres of sea level rise on average, 1.1 metres of sea level rise perhaps at the high end, and 0.61 metres of sea level rise at the low end, compared with 0.43 metres. So even with a low emission scenario, just by the end of the century, the low emissions would reduce the projected sea level rise by about 50%. And by 2300, there's actually a world of difference in the current assessment between the consequences of a high emission scenario, potentially more than 5 metres of sea level rise in the extreme estimates of future sea level, maybe as low as 2.25 metres of sea level rise for the high emission scenario. But if we made a choice to take the low emissions route, then actually we would limit sea level rise to be just at the extreme level, a bit above 1.1 metres. And this is an example of a policy pathway which we could choose, whether it's a low emissions or high emissions, which has a dramatic effect on, so that decision that we might make today has a dramatic effect on the future sea level in 2300. In the last century, the sea level rise actually was about 17 centimetres or 0.17 metres. And that doesn't sound very much. It's a little bit over 6 inches in the old formulation, about half a ruler that you might have used that you can currently buy or at school. But even those small changes can actually have a very significant effect. Think about a 1 in 100 year storm surge. Here we call them a historical century extreme. A 1 in 100 year would sound like it was quite infrequent. And just imagine if we took that 1 in 100 year event and converted it to something that recurred annually. So that's a dramatic change in the risk of a sea level extreme. And it turns out that the 17 centimetres of sea level rise that we've already seen in some of these areas in the Western Pacific, for instance, have already become a 1 in 1 year event. So these black dots here indicate that for these small island developing states, that the 1 in 100 year event is now recurring annually in the year 2000. So what it's telling us is that the consequences of even a relatively small sea level change has changed the risk very dramatically of extreme sea levels. And this is similarly seen in many other places around the world, whether it's in the middle of the India or over on in the South America, Central Americas and other places. Now, one of the points of the IPCC is to make decisions around whether we choose a high emissions pathway or a low emissions pathway. And there are regions where actually a high emissions pathway brings forward very dramatically the constantly sea level extremes recurring annually. And we can take an example, like, for instance, on the coast of east coast of Australia here. For a high emission scenario, it's 2030, maybe 2040. For that same emission scenario, it's a little bit later. If we use a low emission scenario, it will be 2050. So it advances, in this case, the recurrence of an annually recurring high sea level by about 10 years. It can actually be even greater for other regions. For example, in the North Sea, there are regions where we might expect by the middle of the century, 2060, 2070, for a high emission scenario, for that annual return for historical century extremes to actually recur annually. Whereas in fact, for a low emission scenario, they're actually put off well into the future. And the other thing to notice about this figure is that while sea level may be increasing on average globally, there are very specific and regional differences in the occurrence of extremes, and those regional consequences mean that the adaptation and response to climate change is also very regionally driven. There are some new and interesting results. Sea level is accelerating. It's now rising twice as fast as it was prior to 2000. It's quite likely that there will be extremes in sea level by 2100 at the high level of 1.1 metres, on average 0.84 metres. Extreme sea level events that used to occur rarely are actually very common. And in fact, this report was the first report from IPCC that's literally talked about small islands disappearing. Many low coastal island cities and small islands are exposed to risks of flooding and land loss annually by 2050. And these losses are actually magnified if there's no strong adaptive response. There are many ways to actually respond to sea level, and the report actually discusses those. There's protection by the building of hard infrastructure, There's accommodation by lifting some of your assets. There's actually the use of nature-based or ecosystem-based adaptation, the building of dunes, the planting and cultivating of mangroves as a way to protect coastlines. We can actually advance coasts by moving structures forward so that you protect what's behind. And then there's managed relocation or retreat. And you can imagine actually in that 4-day plenary session where some low-lying islands take disgruntled or take umbrage with the idea of a managed relocation of their island population to somewhere else on the planet. So these are sensitive issues. And one of the things that's very clear in the analysis is very often the people with the highest exposure are actually the people who are most vulnerable and often have the lowest capacity to respond. So there's a very uncomfortable intersection between those who are vulnerable, those who are at risk, and their capacity to respond to sea level rise. The oceans, it's not just about sea level rise, it's also about the fact that it's warming. Those changes in temperature have consequences. It's also about the fact that the ocean chemistry is changing. It's becoming more acidic. It's actually losing oxygen. And one of the results that has remained and continues to remain true in this report is that the oceans are a great absorber of heat. And that absorbing of heat actually means that the oceans delay the onset of the equilibrium temperature. And it's because of this role of the oceans that if we were to switch off greenhouse gases tomorrow, we would still warm by another 0.3 to 0.4 degrees because of the fact that the oceans have been absorbing heat and keeping surface temperature at a lower than the equilibrium temperature of a future climate. It turns out that the oceans have continued to warm unabated in the observations, not just in the surface waters, but actually at depth, 2,000 metres, and also particularly in the southern hemisphere in the bottom waters. And that is a signal that's been increasingly, is emerging more strongly, progressively in the various reports. This chapter is very much about the concept of here are the physical changes, here are the marine ecosystems, and those marine ecosystems depend very strongly on the upwelling of nutrient-rich waters from depth. And one of the controls on that upwelling of nutrient-rich waters from depth, which drive the primary productivity in the surface waters, is a concept called stratification. And what we're finding is that the oceans are actually stratifying as they're preferentially warmed at the surface of the ocean. And that preferential warming means that it's harder to move surface water into the ocean interior, and it's harder to bring up water at depth to the surface itself. The stratification has changed only by a couple of % in the historical record, and that might not seem much, but it's enough to make a difference. And those stratification changes will continue on to the end of the century as illustrated in this diagram. Curiously, the arrival of climate change is different for different variables. Imagine the climate having this kind of variability, and then the mean of the climate increasing and passing into a new climate state. Once the mean climate has moved beyond the current natural variability, that is a new climate. It's a new climate state. And what we find is actually progressively that the ocean has been changing its state, and these states emerge at different timings. So ocean acidification has actually emerged very early on, back in between 1900 and 1950, and where 80% of the ocean region has actually emerged out of its natural variations back in 1910. Surface temperature, for instance, has emerged over 70% of the global oceans in the year 2000 or late 1990s, and 100% of it will have totally changed by the end of the century. Oxygen is a key variable. The surface oxygen is moved into the ocean interior. In the year 2000, about 40% of the oxygen surface of the 100 to 600 metre layer is actually decreased in its content of oxygen. By the end of the century, we'll have seen 80% of the Earth's ocean area actually have declined and emerged. And similarly for nitrate that's upwelled into the surface waters and the net primary productivity. So what you can see is actually the state of the ocean is moving from its past to new state, a new climate, but some variables actually emerge earlier than the others progressively over time. And this presents challenges if you're a marine ecosystem that depends on the prior ocean state. So just to summarise, the oceans are continuing to take up excess heat. And in fact, actually, if we project out to 2100, there's still another 2 to 4 times more heat that will go into the oceans over what we've already seen. And if we have high emission scenario, a further 5 to 7 times more heat. This heat that's being taken up, this warming of the global ocean, is actually reducing the amount of exchange with surface, between the surface and the deeper layers. Something that's really emerged quite strongly actually in the last 10 years is the concept of marine heat waves. Marine heat waves are just like a heat wave in the atmosphere. They're events that are hot, much hotter than the current. They're 3 to 4 days or more longer, and they've doubled in frequency. They're much more severe, and there are well-documented cases where those heat waves have led to bleaching in warm water corals. They've led to the decline of kelp forests, and they've altered the distribution of marine life. The oceans continue to take up carbon in the oceans. The picture that's emerging is that the climate is changing, things have emerged, and of course the fish that live in it and the net primary productivity of the ocean has also altered. I'll just talk about the total animal biomass. That's kind of just the living organisms in the upper part of the food web. And the figure to look at, driven by those changing physical conditions, and the figure that I want to draw your eye to is the one on the right here. It's a high emission scenario, RCP 8.5. But the most important thing about this figure is actually its clarity. What you can see, the stippling here, by the way, means that the changes are not significant across the models. These are models of fish distributions. And what you can see here is that there's a very strong decline by the end of the century in the mid-latitudes of the global ocean through to the equatorial regions of the fish biomass. The 30% is actually a lot, and it has consequences on global scale. So the mid-latitudes and the equatorial regions decline almost everywhere. But as Jess was pointing out, in the polar regions, the Arctic Ocean and actually the Southern Ocean, there's actually an increase in the animal biomass. Those projected for the high emission scenario. And you can see if we made a different choice, we made the choice around low emission scenario, you can actually see that the signal of change in the total animal biomass is much, much weaker and much reduced. Now, we can actually calculate as a proxy for sustainable yield a thing called the maximum fisheries catch potential. And you can see in the fish catch potential in the equatorial and mid-latitude areas also declines like 20 to 30%. And if you think about the intersection of these fish catch for those communities that are dependent on, particularly in the small island developing state, the coastal regions, in the equatorial zone, you can see that there's projections, the projections either at low or high, a decline in the total available biomass for fisheries. And so once again, we see this narrative of the people with the highest exposure and vulnerability. For example, the small island developing states in the tropics are often, and coincide with often those with the lowest capacity to respond. Climate change is impacting the ecosystems and their goods and services. And in fact, the report, while we don't talk about it too much here, talks about the threats to key cultural values, dimensions and livelihoods. These changes in fish distribution and animal biomass actually leads to a net reduction in the amount of biomass globally. It's actually telling us that we're going to see a decline of order 20 to 25% by the end of the 21st century in the maximum catch potential of fisheries. So these changes are altering our capacity to feed the world's population from wild fisheries. It turns out that wild fisheries are also managed, and so there's actually, in some areas, quite a reasonable capacity to actually manage those problems. There are other ecosystems where actually we have a lower capacity to manage these problems, and I will talk about those now. Marine ecosystems are often not modelable in the way that we're able to for fish. So what we do is a risk assessment approach. We can look at the warming, the change in acidification, the effects of deoxygenation, the effects of sea level on coast, which has a significant impact on ecosystems, and the consequences of extremes. So we take these things together and through the literature do an assessment across an extraordinary array of ecosystems. So each of these columns represents the different ecosystems that are being covered. We work from warm water corals, the kelp forests, seagrass, epipelagic, that's the surface ocean ecosystems, the rocky shores, salt marshes, cold water corals, and so on, all the way to the deep benthos. The deep benthos, of course, is in the open ocean, but it's actually more connected to the surface waters and changing productivity than you might first imagine. And what we find in this assessment against these hazards is that there are risks of high-level impacts, very high if it's purple, with different levels of confidence. The dots here, once again, like the pictures shown earlier, showing very high confidence through low confidence. And these particular ecosystems have been arranged in decreasing order of vulnerability. The most vulnerable systems on the Earth are warm water corals, and they're the most threatened by rising temperatures. We've already come about 0.8, 0.9 degrees. We're already threatening those systems. Kelp forests and seagrass meadows are also affected, but they're projected to occur later in time. But of all of these systems, you can see they're mostly negative impacts across all of them. So the level of risk is projected to actually increase progressively as global mean sea surface temperature rises from rising greenhouse gases. It's already been observed that there are changes in the ocean causing shifts in fish populations, reduced global catch. There are communities that are depending highly on the seafood, and there are risks both in the quality of the food, the nutritional aspects, as well as the actual security, food security. We can make adjustments, we can adapt and respond, by reducing pollution, and this will help. And fisheries management and marine protected areas offer some opportunities for a response that adapts. I talked earlier about the fact that marine heat waves and similar kinds of events have been understood and has emerged as a new subject in the scientific literature. And there was a particular marine heat wave that really affects Australia in the Tasman Sea. This blob in the Tasman Sea in 2015, 2016 actually coincided with a failure in the spring rainfalls, low levels of hydro capacity in Tasmania. What coincided, unfortunately, with the breaking of Basslink. It also coincided with POMS, the outbreak of POMS degrees in the oysters in the eastern coast of Tasmania, a big decline in the abalone season, total costs and floods actually in the autumn. And all of these things combined together cost the state of Tasmania well in excess of $300 million. Note the currency, 300 million American dollars in that single event. And increasingly, the research community has come to understand that these extremes around the world have very big negative impacts economically, marine ecosystems, and then on the communities that depend on those things. So let me hand back to Jess.
Thanks, Nathan. And I might go straight to the next slide, please. So I'm just going to try to highlight some of the policy insights from the report. It certainly highlights the urgency of prioritising timely, ambitious and coordinated action to address the widespread and enduring changes that are occurring and are projected to occur in the ocean and cryosphere, as you've heard already from Nathan. It also provides the best available scientific knowledge to empower people, communities and governments to tackle these unprecedented transitions in really all aspects of society. The report gives strong evidence of the benefits of combining scientific knowledge with other kinds of knowledge sources, and in particular local and Indigenous knowledge. And also for the first time, it highlights the importance of education and climate literacy to enhance our understanding of these changes and our capacity to respond. So again, as you've seen from Nathan's slides, the report does highlight widespread climate impacts and risks from the tropics to the poles and for people worldwide. And in understanding the consequences of these impacts and also considering options to adapt and respond to them, it's really crucial to consider these effects in the context of other direct human impacts, again, that Nathan mentioned, like pollution, sedimentation and fishing activities. And so if you look across the middle row of this figure here, for example, changes in polar regions to habitats, movement of species into these regions and changes in primary productivity can potentially act synergistically with the effects of pollution and fishing to impact ecosystems. And there's a strong need to develop management approaches that combine annual measures that relate to specific fisheries with broader assessments of future ecosystem trends and shifts in order to reduce the risks of fishing exacerbating climate change impacts for polar marine species, but also more generally for marine ecosystems around the world. I might just, in the interests of time, move to the next slide rather than talking more about this figure, but I'd encourage anyone that's interested in looking at the report to perhaps find that one in the FAQ for the oceans chapter. So some of the key impacts and risks for Australia that require policy responses through adaptation and mitigation include that, as Nathan showed you, many of Australia's coastal cities and communities can expect to experience pronounced changes in extreme coastal flooding events. So once in a century, extreme coastal flooding is likely to become at least once every year by the middle of the century. You saw the graphic on heat waves, and Nathan highlighted that not only are we seeing more frequent extreme events, but they are often occurring at the same time or in quick succession. And Tasmania's summer of 2015-16 is a very clear example of that, with drought, marine heat wave, damage to kelp forests, disease and death of shellfish, and the flooding, which was a significant cost to the state government, but also stretched emergency services, energy supplies, and the aquaculture and manufacturing industries. We are also seeing significant changes here in Australia and climate-driven loss of marine habitats, particularly tropical corals, but also extensive loss of kelp forests and changes to mangrove and seagrass habitats, as well as increased risks for marine industries like fishing and aquaculture. So then what solutions do we have available both in Australia and globally? And this slide here is a figure from Nathan's chapter of the report that not only synthesises a very large amount of information, but also is extremely useful in that it maps out the solutions space, if you like, for ocean-based responses to climate change. And so it provides options to inform decision-making. So in this figure, as Nathan's highlighting, the response options are listed down the left-hand side, and across the top we have benefits of those options, which are the blue shapes, and constraints, which are the red shapes. The circles are global scale options, and the rectangles are local scale options. And the shading of those shapes shows how highly the options score, and the thickness of the lines shows the level of confidence. So there's a very large amount of information in this figure to unpack, but the key things that I just wanted to highlight here are that in terms of reducing the impacts of warming, really the key response options are at the global scale, and generally have high constraints and importantly trade-offs to be considered. But in terms of responding to other impacts, we do have a range of options at the local scale for which there is relatively high confidence about their effectiveness. And so that's that kind of cluster in the middle of the darker blue boxes. And importantly, many of these local scale options have high co-benefits, so that one response is helpful in addressing in multiple impacts or achieving multiple benefits, and that there are relatively low constraints. So then to finish up in this next and final slide, I wanted to highlight that critically, and as Nathan talked about right at the beginning of our presentation, you know, the report is unique in its scope in that each chapter spans assessments of physics, ecology, human systems, and the policy responses. And so there are some strong emergent themes across chapters and some important and unique conclusions. And so with respect to the policy options and solutions, which I've talked fairly briefly about, but which are needed to address the challenges and impacts of climate-driven change in our oceans and polar regions in a timely manner, we need to create conditions to enable effective adaptation and mitigation. And these include intensifying cooperation and coordination among governing authorities across spatial scales and across different planning horizons in time. I highlighted the importance of education and climate literacy, but that that needs to be coupled with an emphasis on monitoring and forecasting, the use of all knowledge sources, including local and Indigenous knowledge, and the sharing of data and information. And finally, there's a need to enable capacity building, particularly for those highly vulnerable locations that Nathan has highlighted, for social learning, for consideration of these complex trade-offs, and also on the more positive side, to be able to realise these co-benefits that might come about from some of the solutions that we have available. So I will wrap up there, and thank you again for joining us. And I think now we hand to Terry to moderate questions from the audience. Thanks.
Thanks again, Jess and Nathan. And yes, we've got an opportunity now to go through some questions. I've got the very simplest question for you while a few others queue up, but it's a question from Estelle. Where can I get a copy of the report? So if I want to read further, where do I go?
You go to IPCC, so SROCC. So if you type IPCC, SROCC, you'll get that report as the top item in your Google search engine.
There's an excellent interactive online version of the report that enables you to navigate easily through the chapters and the summary for policymakers, and is a nice alternative to having to download a very large file.
Thanks, Jess. Thanks, Nathan. So we had a question arrive a little bit earlier from Philippe, and this question arrived, Nathan, when you were talking about those extreme climate events going from 1 in 100 years to becoming almost annualised through some of those Pacific areas. So the question was around, is there any explanation why the South Atlantic doesn't have a future dangerous scenario in comparison to the other oceans?
I'll have to look back at the South Atlantic, but the quick answer is that the change in risk is strongly related to the strength of tides and storm surges. So areas of very high tidal ranges and very strong storm surges driven by the meteorology have the lowest tendency to change. And the South America, the Southern Ocean South Atlantic will probably have the very largest tides and some of the strongest storm surges. And so it tends to be a lower point in the change in the extremes. And the tropics is always a more quiet area, and so the tides tend to be smaller as well. And so part of that means that the historical extremes changes annually for a smaller signal change. And sea level rise is, it's about 20 centimetres over the last century, and that's enough in the tropics to make a extreme sea level rise emerge this beginning of this century, but in other areas it's going to be much later, and the South Atlantic will be for those reasons.
Thanks, Nathan. So another question that's come through relates to Antarctic governance, and it's how are Antarctic governance groups prepared to deal with climate change challenges?
So I can have a crack at answering that one, mostly from a biodiversity perspective, but I guess the framing is that in some ways Antarctica and the Southern Ocean are in a better place than the Arctic in terms of the governance challenges because we don't have to deal with the impacts of climate change on local communities and Indigenous communities. And so there is an element of relative simplicity there, but that's not to understate the importance of managing the impacts. And so in terms of conservation of biota in the Southern Ocean, that comes under the remit of CCAMLR, the Commission for the Conservation of Antarctic Marine Living Resources. And climate change is certainly on CCAMLR's radar, and importantly so because one of the key species they manage is Antarctic krill and the Antarctic krill fishery, and krill are certainly very vulnerable to the risks of climate change. And so, you know, scientific contributions like this report are very important for informing the way that CCAMLR goes forward in managing those risks.
Thanks, Jess. So I've got somebody who joined a little bit late, but they were curious to try and get a little more understanding about ocean alkalinity enhancement and what that might mean.
Yeah, so to respond to that, Terry, the story of ocean pH is very relevant to the story of coastal environments, and in particular our shallow warm water coral reef systems. There's still a lot of evidence that is still needed to actually make a comprehensive story, but there's very clear evidence that the corals themselves they grow with the same dimension, same shape, same structure, but actually there's just less coral in them. So they're thinner, lighter, more brittle structures. And so in fact, the increase in ocean acidity, the lowering of ocean pH, means that that particular life form is likely to be more brittle, more vulnerable to temperature extremes, but also to physical storm meteorological events as well. In the chapter, we actually, whilst talking about coral reefs, one of the solutions that we actually talked about was the concept of rebuilding coral reef systems through the same practices as like in forestry. So actually re-sowing reef systems with artificially grown corals from nurseries as a way and means to protect reef systems. The challenge, and there are laboratories that do exactly that already. The challenge is not whether we can do it technically, the challenge is whether one can actually scale it to a scale that would actually make a difference under the threat of the temperature thresholds that I showed around coastal reef systems.
Thanks, Nathan. A slight step away from pH, but could you explain or give a sense of how plastics in the ocean affect the physics and chemistry of seawater, and does that have any connection to the problems that we're dealing with?
Yeah, plastics. The plastics have no direct effect on the chemistry of the ocean. They have a very direct effect on the composition of the ocean. Plastics are not covered by this report. That's perhaps the first thing I should say. Plastics are covered by the World Ocean Assessment undertaken by the UN in particular, because the focus of the special report in Oceans and Cryosphere is climate change and its consequences. But to answer the question, the plastics will have no real effect on the chemistry. They have impacts, though, on the physical environment that marine ecosystems live in and consume. And so the problem there is kind of peripheral to the issue of climate change, but actually it's one of these compounding events that go together. And so the consequences get a little bit magnified, both with climate change plus the additional presence of plastics. Maybe Jess would like to talk some more.
No, I think that's a great answer, Nathan, and it's another example of a direct impact that humans are having on marine life that can interact in a negative and potentially non-linear way to put living marine organisms at risk.
Thanks again. So again, jumping to a completely different area. So the question for this one is, what effect will the potential increase in fish stocks in the Southern Ocean have on fisheries management and policy making in the region?
So that's an important question, and one that is already being considered by the various organisations that manage fisheries both in the Southern Ocean and in adjacent regions where stocks might be moving from. But it's a complex question, not just for the Southern Ocean, but for other regions of the world too. And in many ways, the Arctic is seeing the effects first and having to find the governance solutions earlier than elsewhere. And you know, it's not necessarily a positive thing from an ecosystem perspective to have new species move in if those species compete with the species that were there before, and also if the habitat for those species is moving even further south, and you know, once they hit the Antarctic continent, there's not much further to go. So it is an important policy question that requires a high level of coordination and negotiation, and the more science that we have to inform what the future might look like, the better place we are to address that.
There's in our particular chapter, there's nice figures of the actual distances that species have moved in the last 20, 30 years. And in the projections I was showing, the level of change is enough that actually in the equatorial area, you'll get local extinction of some species and a displacement to high latitudes of some of those same species. So there's a huge migration implied in those figures, and there are some really nice evidence of that in the Arctic, in the polar regions chapter. It's the world is on the move.
The next question starts with a bit of a comment regarding the positive remarks that have been made during the presentation in terms of governments prompting the investigation of the report and governments really seeking to have the IPCC reports prepared. And then we know enormous global meetings in terms of consideration of those reports. So what's your feeling, both Jess and Nathan, regarding how the report's being heard and the responsiveness to that analysis and the implications that are summarised in the report? So how's that being heard by governments? And really it's a question of around the world.
You want to talk to that, Jess? Very happy to talk to it.
Well, I'll have a crack and Nathan can probably add to my response. I think it's very highly variable depending on where you're thinking about, and from my perspective, in some nations, the report has been given a lot of airtime and considered very seriously, and in other places that hasn't occurred so much. I think, you know, events this year in some ways have highlighted the importance of the findings from the report, and in other ways may have distracted people's and governments' attentions away from the issue somewhat. And I think the other point to make is that this special report was one of a series of 3 special reports, and that there's probably a need for the results from those 3 special reports to be considered together to inform decision making.
So someone else has just commented now, and they've said the report clearly says we need to act now. That's actually correct. We have choices. A high emissions pathway is always worse in terms of marine ecosystems, in terms of human communities, in terms of the overall system than the low emissions options. And if we go back to the SR 1.5 report, there was less than 12 years to turn around emissions, less than 12 years, if society wants to have a temperature below 2 degrees or below 1 degrees. That is a very rapid challenge if society wants to meet it. Scientists like myself, our task is actually to deliver the information. And we do these reports in a way that provides the information that gives a sense of the urgency, right? If the question is 1.5, we must deliver a reduced emissions pathway in just 12 years. So that's right on the horizon. You can see that the impacts on some ecosystems, like warm water corals, actually we're right at the cusp of crossing key thresholds for those. It's a little bit later for some of the others. So I think it's correct. We need to personally, globally, the world over, increase our ambition around emissions. But as scientists, our job is actually to deliver policy relevant, but not be policy prescriptive.
Thanks, Nathan. Thanks, Jess. It wouldn't be, we're getting towards the end of the question list, but it wouldn't be a COVID-19 period without a COVID-19 related question. So we might look to finish up with this question, but what do we learn from a COVID-related lockdown? And first, and this is a very difficult, complex question to even contemplate, but first is the potential window for change and opportunities associated with the lockdown. There are pieces around we're seeing in terms of some immediate environmental improvements. So what are the scientific insights that could be gained that would help rethink the science and governance issues as we're pondering through this lockdown period?
I'll venture a comment while Jess is thinking. There was a very interesting event historically, which was the global dimming event, when there were actually, because of the volcanic eruption in Iceland, there were no planes flying. It's a little bit similar to the current moment. But actually, atmospheric scientists were able to figure out that there was a dimming of the, so there was an I've forgotten the sign, but there was a dimming, there was an alteration of the temperature that actually coincided with that absence of aeroplanes flying because of the reduction in high altitude vapor trails. There will be similar papers very shortly, actually, as a consequence of the reduced emissions, as a consequence of the reduced aerosols in the atmosphere, and how that has altered the temperature. And the response of the Earth is pretty quick to those events. And so I think in the context of this question, it will be clear that actually there are many benefits of reduced aerosols in the atmosphere, which have health benefits, societal benefits, and these may actually have a different value to the way they have had in the past. So I think the current unfortunate circumstances is that it will lead to an insight about what a future without emissions might look like in terms of the atmosphere and perhaps in terms of reduced impacts. So it's perhaps a glimpse of a possible future.
Thanks, Nathan. Jess?
Yeah, no, I would offer two brief comments in kind of at least partially in response to the two components of that question. The first is that I wonder whether the the policy window that might emerge would be, you know, as we emerge from lockdown, and in some ways we have pressed the reset button and have opportunities to think about how we do things slightly differently. And I think it will be very interesting to see how that plays out in relation to climate change. And the second observation, which is not a novel one, and the audience may have seen or heard it elsewhere, is just that, you know, COVID-19 is a very clear demonstration of how we are able to act rapidly to address global scale challenges in a way that's informed by scientific evidence. And, you know, that is clearly very much what is needed for climate change as well.
Thank you both. There was just one question that Bindu had asked, which you don't have to answer because I'll come back to. Bindu was asking when might there be an opportunity for webinars like this to be heard in Southeast Asia, and particularly being from Nepal. These are, and just touching base to let you know, this was a seminar that was available all around the world. Tonight we've been joined clearly from people in Australia, but Canada, Sweden, Germany, Norway, New Zealand, Indonesia. So a number of countries have been able to join in to listen to what I must say in terms of living and being in part of Tasmania, a couple of our extraordinary scientists. We know that Hobart and Tasmania is home to a large group of outstanding international marine and Antarctic scientists, and it's a wonderful place to be. It's clearly globally represented in terms of IPCC reporting as a community, and something for which we should be very proud. Just in closing, I wanted to do a couple of things, was to thank, and again with silence, Jess and Nathan for their presentation, congratulate them on their achievement in terms of authorship. And I also wanted to thank the UTAS team who put together tonight. I wanted in particular to thank David Benook, Belinda Brock, David Ottman and Richard Quinn for the work that they do behind the scenes to make sure that events like this happen and happen successfully. And finally, I did want to also just let people know that, as mentioned, this was the inaugural Island of Ideas webinar for the University of Tasmania. There are plenty more coming, which has been the slide that's been in front of you over the last while. Please feel free to jump online and book into those events. It's a wonderful way for us to be sharing great information across a broad audience. And again, we'll be trying to do this not just within Tasmania, but again, taking Tasmania to the nation and to the world in terms of the outstanding science we deliver. Thank you, everybody. It's been a great presentation, and have a great evening. Good night.
Good night, everyone. Thank you.
Good night, everyone. Thank you.